Well, hello, my name is Sam Abrahamson.
I'm Cory.
I'm Matt Schiroo.
I'm Theis.
And our capstone project for the spring semester is the Horton Spun Metal Pulley investigation. So our agenda today, we will be discussing an overview of our project. We will talk about our project objectives and deliverables that we were given from Horton. We will talk about some design criteria. We'll talk about a system breakdown of how we believe the spun metal science should be performed. We'll talk about some preliminary designs which we were given from Horton, and we will talk about future improvements to the process that Horton can use. Here is our deliverable summary. We were given 5 different deliverables which were completed would constitute a successful project. Our first deliverable would be a review of base materials that can be used for spun metal sciences. Then we can talk about some characteristics, the availability of those materials and the cost. Our second deliverable was to deep dive into the limitations of design when creating spun metal parts. Our third deliverable is create a world review of the biggest and most sophisticated manufacturers of the equipment, like machines that can be used to spin metal. Fourth deliverable is a cost-benefit analysis, putting against Horton performing the spun metal process in-house versus an outsource. And our fifth deliverable is a list of experts in the design and manufacturing of spun metal technologies. Okay, and an introduction to Horton. Horton Incorporated is it's an American company. They're a major truck OEM. OEMs are original equipment manufacturers, so they create components which other companies can purchase to put into larger systems and then into their own practices. Some of their on and off highway customers include John Deere, Daimler, Volvo Mack, Peterbilt, Caterpillar, and Komatsu, so big, large trucking industries.
All right. So now we'll take a look into how this is incorporated into Horton, what products that they manufacture, how this project ties into that, and some of the work that Horton has done in the past. So the part that Horton makes that goes on these OEM trucks and agricultural equipment are the fan systems, the clutch drive systems, and pulley systems that go on the front of the engines to help in the cooling of these large equipment. Now the cooling system is made up of a variety of different components. You have radiators, you have fans, you have all the coolant, there's water pumps, heat exchangers, all the stuff that goes in for keeping the engines in proper operating temperatures. Now these components are all driven off of a belt drive that goes on the front of the engine. And now the cooling system turns on and off with the clutch drive so that the engine can stay at proper operating temperatures so that you can achieve proper fuel economy. And this is all done to increase the reliability of the equipment and the tooling. The current process that Horton uses for making the pulleys and the front drive systems is a cast metal process. So they used a sand cast piece, so on the top left photo you can see a sand cast mold. In that mold, molten metal is poured, and out of that you get a cast piece or cast blank, which is the top middle photo. As you can see, it roughly resembles a final product, but it's very rough in shape and takes a lot of machining. The machining operation takes away a lot of the material. It has a lot of waste and scrap. But what it does is it achieves your final part, which is the bottom left, or a pulley that we'll be focusing on. Now, that pulley is one of several pieces that go on the front drive end of an engine. Some go to the water pump, some go to cooling fans, some go to alternators and other pieces for the equipment. The proposed process that we'll be looking at is the spun metal process. Now, this differs from a cast process in the fact that all your material comes in sheets or coils. These coils are unrolled and then they'd be stamped or potentially laser cut or sheared into circular blanks. These circular blanks are then spun or drawn over a mandrel or buck into the desired shape. Now, the process can also take on annealing steps that help soften and take some of the strain out of the part prior to final rotational forming, which puts things like the grooves in for the serpentine belt that drives all the fans. Finally, you can have heat treating processes which help achieve desirable hardnesses. Now, the metal spinning process is fixtured on a blank or a mandrel. Now that's in the shape of the part that you'd like to achieve. On this mandrel, you would put a circular disc of your material, and that is spun and forced over it with a CNC or by an operator. And they use rollers or shoes to push the material into the shape, slowly forming it into the final product. In the pulley configuration that you see here is one of the actual units that Horton produces. The one that we'll be focusing on is in their clutch drive. The clutch is attached to the fan itself, which is up in the very front of a machine next to the radiators. In the past, Horton has done several CAD designs, different modeling, to try and see and predict where failures and stresses would appear in their final product that they'd be making. The photo on the left shows where under load the maximum stress would be, which is on where the material has done a complete 90-degree bend, going from its vertical mounting surface to its horizontal surface where the belt actually lies. The picture on the right shows where the maximum deformation under loading is. You can see the very outer lip of the pulley, furthest away from the mounting surface, has the maximum deformation, and that's caused by all the force of the front drive system. So this is a video that Horton has taken in the past for one of the processes when they're making prototype spun metal parts. So the way you can determine how if your process is capable or not is to do some destructive testing. So the photo on the bottom left shows some spun metal pulleys that Horton had made that go on a test rig. This test rig is just spun by an electric motor, has a serpentine belt, and it tests the longevity that the spun metal parts would last if they were installed on a final product. They saw through the testing that they saw complete failure of these parts between 80,000 miles and 170,000 miles, which may sound like a lot, but in general, it's pretty low for the amount of miles that some of these equipment may see, which may be up to millions of miles of road use. Here is a final photo showing where that failure point occurred. We can see that it was on that bent lip where our highest stress concentrations showed up in the FEA design. So it's good to see that our modeling and final results have correlations, but it's bad to see that our part is actually failing prematurely.
So next we're going to do a deep dive into Deliverable 1, which is a review of the materials. So on the next 3 slides, we just have some technical information about 3 common types of steel that we think would work very well for Horton's application, both in the pulley and in the spun metal process. So first we have 1006 steel, next we have 1008, and finally we have 1018 steel. All of these work perfectly fine in the metal spinning process. They just have differing times and amounts of how quickly they harden while being worked on. Some other information about materials is stainless steel is also a viable option for metal spinning, but it is 4 times the price. So we don't think the benefits of stainless steel will negate the 4 times price increase in the material. If you are going to use stainless steel though, 3000 series is the best for metal spinning. Some other types of regular steel that will work great for spinning are 1009, 1010, 1018, and 1024. There are other possible options for metal spinning, such as copper and aluminum, but these metals will not be strong enough to withstand the stresses put on the pulley. So some science behind metal spinning. Here we show 3 general shapes for metal spinning and the guidelines that go along with making each shape. So the most important details in almost all shapes are the outer diameter, the height, and the radius of the bend. Horton's pulley currently fits within all of these given guidelines, so this should not be a limiting factor in the creation of the pulley. There is other shape guidelines that will be put in the report. These are just the 3 that are most applicable to the pulley itself. Some other information about metal spinning, we have the maximum size of the sheet that can be spun is 92-inch diameter, because that is the biggest sheet that can be ordered without welding. You never want to spin a welded part. Metal spinning is a very safe manufacturing process, but if you start spinning welded parts, that's where you can run into some dangerous situations. As a guideline for strength, the material should only be stretched as deep as it is round. If you put too much of a draw depth on the part, it can severely weaken the final product. If you use aluminum, aluminum can be stretched basically as far as you want without problems, as long as it reaches a minimum or stays above a minimum thickness. And for steel, the thickest steel that ACME has ever spun is 1 1/4 inches, but they believe they can do up to 1.5 inches without a whole lot of problems. So some limitations of spun metal. We had some shape limitations from a few slides ago. And besides that, when you're doing the metal spinning process, if the material gets too thin, or if you use the rollers too fast, you can have some serious issues such as wrinkling, ripping, and stress fractures. Any of these failures will cause an instant scrap of the part. It is impossible to save a part that has any cracking in it without melting it down and starting from scratch. So you can have some potential production volume issues, balancing out going in too fast compared to getting parts that'll work strength-wise. So for quoting metal spinning, metal spinning companies will quote a design based on perimeter and a draw depth of the piece provided. So in a general guideline for the equation of the sheath that we were presented is the diameter times 1.5 times the draw depth. The blank cost is calculated based on the weight of the piece. That's impossible to get an actual price because the metal prices fluctuate so much. So it's just based on the estimate at the time you want to make the part. So for the changeover and runtime in the setting up of the process, the entire process will take about 6 minutes for this specific part. That includes the loading phase, the turning phase, removing the part from the buck, and new piece setup. And a machine at full capacity will produce about 400 parts per 40-hour work week. That can be adjusted, but this is set at a pace that we think will have minimal problems with wrinkling and stress fractures. So another process previously mentioned is annealing and heat treating. So the benefits of annealing are it softens the metal for cold working and prevents hardening and stress fractures, which improves the machinability. It'll also enhance the electrical conductivity, but in our case, it seems very important due to the stress fracture breaks the first time Horton tried to make a spun metal pulley. So we would highly recommend annealing during the process. When the whole process is over, you can heat treat it to increase the hardness, lower the ductility, increase the toughness, and strength, which will overall just increase the structural stability and the longevity of the part. So pass it on to Cory.
During our time doing research for this project, we decided to tour ACME metal spinning to get a view of what these machine shops actually look like. So this slide, we're going to talk about what we observed pretty much while we were doing research at ACME. Right when we got in there, we went into the floor and got to take a look at their entire process. They had multiple machines running, and we were able to be out there without any hearing protection. It was so quiet that we were able to have full conversations, which is a benefit of metal spinning for communication between employees. A few of the things they recommended in processes was always deburring metal before you spin it to help prevent the cracks. One thing that they said when they looked at the video from Horton was the pressing that they do is really quick and aggressive, and that is likely what's leading to the break in the part. They also recommended rolling machines in both directions, or rolling the material in both directions. What I mean by that is like a pottery wheel where you move the material back and forth to help put more distribution in the metal so you're not getting as thin and thick differences in the material. Slowing down and lowering the pressure on the presses would also help to likely not fail the part that we're working on. Another part of the machining is a roller. The roller is the tool that pushes the metal across. The rollers are one of the more difficult parts of this. They're hard to find. You have to build a lot of them on your own. That requires somebody who is knowledgeable in metal spinning, has been practicing it for years. The angle of the roller is the biggest issue because as you push the metal across, it can come up over the roller and that will lead to a stress fracture or wrinkling, and now you have to scrap your part. So this is one of the biggest issues and hardest parts of metal spinning is the rollers. And like mentioned before, annealing is something they recommended for removing stress in the part. One of our deliverables was talk about machines and that we found in our research for using for the metal spinning process. We have 3 companies that we recommend. On this slide, we're going to talk about the different types of machines that they have. There are single and double rollers. The single roller pushes on one side of the part as it spins around to move the material across the buck. The double roller has 2 rollers, one in front and one just a little bit behind it for moving the material across. This puts more distribution in the stresses that you're applying to the part and helps your process times quite a bit. One thing with the bucks that they talked about was making them out of elastic material, because as you press the metal down onto the buck, it likes to spring back when you move the roller back across. So you want to have a elastic buck to a point, not super weak, but something like wood works very well. As you press in, you're also pressing into the buck, and when you release, it springs back to the size that you're desiring. One of the machine companies that we looked at is Lee Tip Top. They're based out of China. They are a CNC spun metal machine manufacturing company. They produce both single and double rollers. Down here below are just some stats about their company. Here is a video that we have of one of their machines. In this video, you can see them place the metal onto the rollers. And as they push it across the buck, this is a double rolling machine. They have one roller on one side, one roller on the other side, applying even pressure on both sides. One roller is right in front of the other one, so you're able to do 2 spinning operations at once as you move the metal across the buck. Very quick, very efficient, and very quiet as well. A couple of the other manufacturers that we ran into. This one is one that ACME recommended to us that they have heard about. It's based out of California. It's called MJC. They are a little bit higher end, a little more expensive. A lot of their machine kits come with both single and double rollers available, and they have a lot of robotic arms that function with their machines for more automated processes. The ones that we got to see in action when we were at ACME was the Prism machines. They're based out of Canada. They're quite a bit more cost effective, and very applicable for the design that we're looking into right now. This is the machine that we're recommending later on in our presentation. Along the side, you see all the stats that go with this particular machine. And most of them that we saw in action were single roller.
Right. Now I'll be discussing the fourth deliverable, which is the cost benefit analysis. So first we'll discuss Horton's current process. So as they stand, Horton produces a single pulley for about $35.67 per unit at a production rate of 10 parts per hour. When we went and discussed with Horton, they believed that they could go off of a 7-year return on investment for the project goals that they had in place. And they would like a new production rate to be around 3,500 parts per week. Here's a spreadsheet of some of the most important factors that we determined to be in our cost benefit analysis. So some of the, on the far left column here, we can talk about the Prism machine, which is the company out of Canada. They create the cheapest machine that we found, maybe not the cheapest, but the most cost-effective machine for what we would need. The machine setup, the part setup, the machine capability, machine specialist, how much it would be to employ a specialist, the type of material, and the annealing and heat treating processes. So for each of these different criteria, we went off of a single time, single week, single year, or single batch / load. So for the cost of a Prism machine, this is a macro level, so this is very average. It's about $400,000 per machine. To set up a machine, the company that we have been working with, ACME, gave us a quote that there's a 2-hour minimum fee for an installation. So that means that when you need to change out the buck, change whatever specific production criteria there is for each new part, it'll take about 2 hours. And we came up with a total about $62 for that, based on how much it would cost to pay a machine specialist, because he would probably be the one to perform that. We were also quoted a part setup time of 6 minutes. As Matt talked about before, there's 4 main steps, which is the initial part setup, the turning process, and then the unloading process. There's another one. Then for this particular machine, its capability is about 400 pieces per 40-hour work week. And we're roughly estimating that a piece of spun metal should be about $6. A machine specialist, depending on where they might be located, could average about $65,000 a year. And we were also quoted the material cost of 1018 steel is about 45 cents. We were able to weigh our part, and we determined that it weighs roughly around 2.86 pounds. So if you produce 3,500 parts per week, that would cost about $4,500. And for the annealing and heat treating process, we were also quoted. For one load, you can heat treat from 1 to about 500 parts, depending on the size. And there's a flat cost of $400 for that load. So if we want to heat treat 500 parts per load, it would take about 7 days to do the $3,500 weekly goal. Next, we'll go over a qualitative analysis. We judged pros and cons of Horton continuing to do their spun metal process in-house versus what it would take, what were some of the pros and cons of them outsourcing. we decided, we did this as a group. We came up with the pros of Horton. Continuing to do their process in-house would be a lower cost per part. There wouldn't be a shipping cost. They would be able to directly oversee quality. There wouldn't need to be quite as much communication, at least over the phone. The engineers might be able to just go down to the shop floor if there is an issue. They wouldn't be able to see if they outsource things. They have to communicate with somebody else, which is more difficult. More parts would be able to produce than the current process, and there'd be less scrap with the spun metal technology in general. Some pros of outsourcing this, there would be professionals working on the parts constantly, and they're most likely going to be leaders in the spun metal industry. We have an asterisk by this, but we believe that it would be less expensive in general to outsource, because you wouldn't have to hire a new employee and train them, and there wouldn't have to be downtime of moving machines around your facility. Also, they would be able to oversee the manufacturing of parts in the bucks if they outsource it. The outsource company would know the best materials and processes needed, since they're already spinning metal in-house. They would already have the necessary equipment, so they wouldn't need to go out and buy anything. If failures arise during PPAP, they'd be the first in line to solve these problems. And then some other similar pros as Horton producing it in-house would be there's less scrap. And a pro for Horton at least would be that if an outsourced company takes on this project, they would absorb the risk and the failure cost if they were to not produce weekly goals. And here's some cons. If Horton produces the part in-house, they would potentially need to purchase multiple expensive machines to meet their demand. There would be an extensive learning curve. They would have to teach all of the new hired employees how to spin metal. They'd have to teach them about the spun metal technologies in general. They would need to either train new skilled operators or hire new operators, find new operators. Spun metal technologies is also very difficult because it's very trial and error based. We showed you several videos of the spinning technology, one from an actual metal spinning process and then one from Horton forming their metal. We did get information that the video from Horton, they're spinning it just too fast. They haven't probably performed any of the trial and error based processes, so that's why we believe it is failing. There would be downtime for installation. It'd be potentially difficult and expensive to produce the rollers. Lots of crossover time. And the last one is all CNC operators may need to be repurposed, because that's what the majority of the operators are in their facility currently, are CNC operators. They may have to go back to school, and there may be possible layoffs, so it could be very expensive for Horton to do this. Some cons of outsourcing this: there would be a shipping cost. They would not have as tight of a control over quality. It could be possibly slightly more expensive to do this than it would be in-house. There could be supply chain risk. There could be communication breakdown. They don't know if or why there might be line down. And there still will have to be trial and error, because with new products, you need to do testing. And for our fifth deliverable, we were needing to find a list of experts who know about metal spinning already and who could be potential customers or suppliers to Horton. So here's a list of 3 professional metal spinning companies that we had found in Minnesota. One is C&W Spinning Incorporated. They're located in Maple Lake, Minnesota. Glenn Metalcraft is in Princeton, Minnesota, and Acme Metal Spinning is in Columbia Heights. Acme is the one that we actually went and visited. It was kind of tough. We actually had meetings scheduled to meet with all three of these companies, but due to coronavirus, we were only able to meet with one, which is unfortunate. And here's another list. We also discovered a list of professional metal forming experts. It's called the PMA. Everybody in this association is 9001 certified. So they kind of meet Horton's criteria of who they would like to supply their products. These three companies are located in the United States. So just need to communicate with these companies to fulfill work. And we can do a summary. We introduced our project. We had a brief explanation of the metal spinning technology in general and how it worked. And then we went over our deliverables, discussed each one of these in depth. Any questions?
So I guess the biggest question I have is the whole purpose for Horton to do this. Was it quality? Was it cost? Was it both? I mean, what was their primary reason for looking at this spun metal? I know it wasn't working. They tried it before. It didn't work very well. But is it truly cost effective, or is it just the quality that's so much better?
The main reason for this was they had a projected cost that they have a higher demand going in the future. Right now, they have dozens of CNC machining operations in-house, and they're only able to produce 10 parts an hour, where with the spun metal process, one machine is able to produce the same amount as their entire factory. So if Horton switched over to a spun metal process, they could potentially meet that future demand that they're seeing and do it at a much cheaper cost.
Yeah, what's the quality difference between the spun metal and the way they do it now? Is there really no difference?
That's the hope, is that they'd be able to achieve a spun metal part that meets that same quality. Right now, with the testing they've done in the past, is where they've saw spun metal not quite meet that level of expertise that they need. But by going with an expert, or just, doing further testing and further processing, then once the two processes have the same level of quality, then it'd be, that's a product that they could stand behind.
Do you know if they outsource a lot of their other stuff now, or do they do most of their stuff in-house?
From our tour there, it seemed like most of the actual metal work was done in-house. They outsourced the metal spinning the first time they tried it because they didn't have the machine capability to actually do metal spinning.
Seems to me they're a pretty good sized company, and it wouldn't surprise me if they would shy away from outsourcing it and try to do it in-house. Just my feeling. I don't know what your perspective is.
That is a possibility, and why we looked into it. Just when we were looking into metal spinning, it became very obvious that you need people who know what they're talking about, or you're going to have a years-long learning curve trying to produce these parts correctly. So we recommend that, at least in the beginning, outsourcing, which will give you more time to learn about metal spinning. Otherwise, like, all the employees at ACME that we were able to meet with, as far as like the metal spinning workers themselves, had been there 10 years or more. They have not very many people who know how to metal spin unless you've worked at a metal spinning company before. And that's going to be the hardest learning curve, along with producing the rollers and bucks on your own. Is a very protected secret by these companies. So it'd be very tricky to do that in-house.
It may be a well-known science, but it's not very well documented. So all the technology that there is very proprietary, and many of the companies don't want to share because they want to be the leading experts. So like we said, all of these technologies and sciences, it's very trial and error. So you have to put time towards working at this. And Horton is expanding as a company. They have a new facility opening soon. And this might be a very critical project for them moving forward, because their new facility might be able to overtake this project and really work at the metal spinning science. So,
Well, I like the recommendation you're saying that, hey, why don't we outsource it for the time being and then see if it's something that we can eventually bring in-house with the right resources and the right talent and the right processes. So I like that recommendation. It's probably not a bad one.
There's no way they could get around either hiring experts in or outsourcing this product. It's too finicky of a process and too difficult to perform without an expert who's been practicing this. When we toured ACME, they had people working in there, and they apprentice for years before they're left alone to operate machines and lines on their own.
I think they said it was like 2 or 3 years working behind someone before they were allowed to make a part by themselves.
Yeah, so it's very steep learning curve with this process.
Well, even a CNC metalworker is a lot of times that's an apprentice job too, but there's a lot of those out there. There's probably doesn't sound like there's a lot of spun metal machinists out there right now that are qualified, I guess, or skilled.
They said that was part of the issue with hiring people, is that you can't go get degrees in this and then hop in to the job and start performing at a acceptable level to meet design criterias and things like that. It takes tons of time to learn.
Like more of an apprenticeship type of job learning. Okay. I don't have any other questions. Anything else for me?
Just wanted to bring up that we would have liked to meet with the other companies in Minnesota when we had plans to do it. So it might be worth checking into in the future and collaborating with those other companies to make sure that they have the same opinions that ACME did. But we felt like the information we get from ACME seems very reliable.
Are you scheduled to do the presentation to the folks down at Horton yet?
We are still trying to get in touch with them to set up a time to do the presentation.
Yep. Because send me a copy of the recorded presentation. What I'm going to have Ben do in the department is consolidate all these and post them out there so that all the students can see all the other ones that they wish to, and that all the sponsors can also view all the presentations if they wish to.
We did want to give a shout out to ACME Metal Spinning for all the help that they gave us and all the information that they helped us with this project too.
Yeah, that might not, and that's something else we might get Beth to send a quick thank you out to them too. There's a couple others that helped a couple of the other projects too, so that's a good idea. Okay,
all right.
That's all I got. Send me the I think you said you already sent me the PowerPoint. That's great. Send me the link or a copy of the video, and then the final report is due by the end of the day next Friday.
Okay.
Thank you.
Good enough. Thanks, everybody.
Take care.
Yep.
Stop the recording.
Yep.